What if I told you that a single spacecraft, powered by just 400 watts of solar energy, has unlocked secrets of the largest planet in our solar system? From volcanoes spewing fire on Io to mysterious storms that rage deeper than Mount Everest is tall, NASA's Juno probe has revealed a Jupiter we never imagined. And what it discovered might change how we understand not just our own solar system, but giant worlds across the galaxy. Eruption Juno has also caught a glimpse of Io in the infrared. The hot spots showing where there is volcanic activity on Io spews out 1 ton of particles in an orbit around Jupiter per second. It moves through the plasma torus and the magnetosphere of Jupiter. This creates a flux tube to be present between the planet and the moon. A flux tube is an electric current which moves through a cylindrical tube of magnetic field lines. It's extremely powerful. It can build 400 0 volts and 1 million to 5 million amps of current. Juno was able to obtain extremely precise measurements of the flux tube during its 12th orbit as it went straight through it. No, this didn't zap the spacecraft because the flux tube has a big diameter and so it is not concentrated enough to hurt the craft. Also, Juno was in and out in seconds. Now Juno, a huge spacecraft 20 meters in diameter, and it literally has to be because it's a solar-powered spacecraft randomly receives 4% of the sun. It would do around Earth. This means, although these panels are gigantic, it can only produce just over 400 watts, but you'll also see that this design combined with the fact that Juno spins gives it a bit of a fidget spinner look. This isn't merely to create a pretty spinning spacecraft. Juno was specifically designed to sense some of the many fields and particles in Jupiter's vicinity, and an enormous spinning radius on a spacecraft assists with that. This is especially clear with this device. Here, the magnetometer on the end of one of the solar panels, responsible for charting Jupiter's magnetic field using Juno data. We now possess an extremely detailed chart of Jupiter's magnetic field, and it is becoming increasingly accurate with each orbit. As one would expect, Juno confirmed that Jupiter possesses a dipole-like magnetic field, but it is not particularly well aligned with the rotational axis. What was of great interest, though, is that researchers found something referred to as the Great Blue Spot, an area on Jupiter where the magnetic field is highly concentrated. Comparing data of Juno's magnetic field with that of earlier Jupiter missions, such as Pioneer, Voyager, and Galileo, has also provided a first for the solar system. Jupiter's magnetic field topology has been seen to evolve very slowly over time, which is referred to as secular variation. Interestingly, this was most visible near Jupiter's Great Blue Spot. This variability is believed to be caused by an area at the very bottom of Jupiter's atmosphere, which we will come to eventually change from a mixture of the strong magnetic field and the ionized particles in the plasma torus, so that Jupiter boasts the solar system's most luminous aurora with radiant power of 100 terawatts. Similar to Earth, aurora look like bands at the north and south poles, but in contrast to Earth, these aurora are only visible in ultraviolet and are only generated from alternating currents and not direct currents. When Juno quantified the power that is created from the direct currents in Jupiter's magnetosphere, wasn't even close enough to explain the luminosity of the aurora, that scientists began to remainder of the power is coming from alternating currents. At this time, it is believed that these alternating currents are produced because of the turbulence in the magnetic field, especially at the North Pole. The magnetic field lines are much more complex, which interferes with a direct flow of currents. This is evident when comparing the North and South Pole aurora. At the North, the aurora is much more dispersed, looking more filament and flare-like, while at the South Pole, where the magnetic field lines are less wavy, aurora appears to be more organized and spherical. What you will also observe is this bright spot and tail on the aurora. This is clearly where the IX tube intersects the planet. What isn't immediately obvious, however, are these other spots. These are from the other large moons in the Jovian system, Europa and Ganem. So, while not as powerful as Io's flux tube, these other moons have their own flux tubes connecting them to the planet. To the magnetic field of Jupiter brings us nicely to one of the main science goals of Juno, to figure out the interior of Jupiter. Since Juno arrived, previous theories have had to be complete. A list out the window by the information it is gathered previously. The idea was that there was a dense core and then a clincuto line between the core and the subsequent layer, the metallic hydrogen layer. The cloud layer was then only conceived to be few hundred km deep at most, but according to the Juno data, the atmosphere off Jupiter goes 30 kilometers down, and beneath that there is an ocean of metallic hydrogen all the way to the center, and even if there is a core, ivory vague, possibly blending into the metallic hydrogen layer. So technicalito, say Jupiter, unlike gas giant, is slightly misleading because 80 to 90% of its radius is thought to be a liquid today, or technically and electrically conduct in plasma, be kind of the same as liquid mercury. Here the pressure is so immense that the hydrogen does not maintain its molecular form with to join protons and electrons, and instead they dissociate at meaning positive and negative charges can travel about becoming an electrically conducting material. We say believe because we haven't been able to make metallic hydrogen in the lab yet. The pressure required is millions of times the atmospheric pressure of Earth, although we have a reason to believe this must be so based on Jupiter's strong magnetic field. In order to generate a magnetic field as strong as this, the dynamo must be generated in an electrically conducting material. It can't be a denser metal, such as iron, in the core of Earth, because Jupiter is not so dense for that. In fact, we know from its density that it has to be composed mostly of hydrogen and smaller quantities of helium, very much the same composition-wise as the Sun. Another reason for the strength of magnetic field is because of the fast rotation of Jupiter. One day on Jupiter in the outside and only lasts around 10 hours. Several forces from this agitate the liquid and stir it up, which produces the dynamo. It is the magnetic field spinning from which we can time a day on Jupiter, because simply observing Jupiter's visible bands couldn't provide you with a certain answer, and that is why you will see these bands appear very strange, moving in opposite directions from one another in different speeds. But that isn't quite so odd if you take into account the invisible jet streams on Earth. What is impressive though, the turbulence and colors present in these bands. So let's have a look at trying to figure out what's happening from studying these Juno images. The cloud layer you are looking at here is the ammonia cloud layer, some air white. These are new clouds, most probably just lifted up from the lower regions of the atmosphere. On the other hand, whereas the red hues you observe are also ammonia clouds, these clouds have reacted with UV radiation from the sun. Consider it to be a photochemical smog. The reddish smog which you observe during some above major cities, the coloring component isn't precisely identified, but in simple words, that the longer it's exposed to the sun, the redder it appears. Interestingly, though, compare these bands with what you can see at the poles, you'll find it's a lot bluer. Here this may be due to UV light not getting here as easily as compared to the equator. Taking a close look, you'll also see what's referred to as pop-up clouds. At first, these were believed to be possibly water ice clouds, but they might be ammonia clouds as well. They are the potential precursors to thunderstorms on Jupiter. A radio wave instrument on board Juno does measure lightning on Jupiter, but these storms are curiously more localized toward the poles rather than at the equator, and more toward the North Pole than the South Pole. The reason for this I sunk down observing closely at Jupiter. You'd be hard-pressed not to see the breathtaking vortexes and storms through Thouthas had a chance to fly directly above the Great Red Spot, where it found something quite fascinating. It was already known that the Great Red Spot rises above the cloud deck, but scientists didn't know is how deeply it extends into Jupiter's atmosphere. The onboard instrument of Juno, intended to look into the atmosphere, has a depth range of 350 kilometers, and it appears that the Great Red Spot reaches down even deeper than that. Also noteworthy is that the spot is colder than the surrounding material up to a depth of 80 kilometers and deeper than that actually becomes warmer than the surrounding material, this heat quite possibly propelling the storm. It has been speculated that the Great Red Spot is a permanent entity on Jupiter, but we've only had around 400 years to watch it so far, a blink in astronomical time scales. Looking over the poles, other potential permanent features have been seen compared to Saturn, which has a hexagon on one pole and one vortex on the other. Jupiter has 5 vortexes surrounding the South Pole, and 8 surrounding the north. It's difficult to say exactly how permanent these storms are, as Juno has only been there for 3 years, and Juno was the first time we have really been able to have a good look at Jupiter's pulse, but they have been reasonably constant throughout that time under the ammonia cloud layer. It's thought to be a water ice cloud layer, although this has not been confirmed, as this layer hasn't actually been seen yet. This is one of Juno's science objectives, though, and it carries a number of microwave detectors in an attempt to locate this elusive material. Jupiter produces heat from inside, which can be imaged using an infrared camera, the denser sections of the cloud layer inhibiting some of the heat from being visible. Likewise, Jupiter to emits microwave which hypothetical water clouds would absorb, so in principle Juno should be able to find where the water is located in the atmosphere of Jupiter by looking for where Jupiter's microwaves aren't visible. Even though this information hasn't been made public or nothing has been discovered yet, all that aside, Juno has still got a while to go on this mission, and no doubt the information it gathers will be scrutinized for years to come. Our knowledge of Jupiter is slowly growing, and with this information comes more knowledge of how our solar system was created, and also that of other solar systems with Jupiter-sized worlds, and maybe Jupiter will surprise us a few times more. But it's been 6 years that Juno started orbiting Jupiter, and in that time, the probe has been hard at work collecting amazing photos and information about the gases. Giant veterans of this channel may remember videos I posted on the 1st and 3rd anniversaries of the mission, but much has occurred since then. In 2021, Juno started its extended mission past the originally intended 37 orbits to include flybys of Jupiter's icy inner moons named Europa, and ultimately, it's been more than 2 decades since Galileo stopped by these moons, and by examining changes within them, NASA is trying to determine what could be happening beneath their icy crust sand without spilling the beans too early. That seems a lot also due to the probe's high-power Juno cam and its stellar reference unit navigation camera. Juno is capturing some of the best photos we've ever had of these ice moons, so with the long-running missions coming to an end on the horizon, as NASA will be decommissioning the probe in September 2025, now seems like a good time to ask, what has Juno seen? I'm Alex Mullen, and you're watching Gastram. Join me today as we view the stunning highlights of Juno's extended mission and unpack the surprising discoveries that are already changing our understanding of the Jovian system. Let's start with a quick recap. Juno launched from Cape Canaveral, Florida in August 2011 after traveling for 5 years, and a 0.8 billion km. The space probe entered orbit around Jupiter on the 5th of July 2016. After having finished most of its primary missions, NASA extended Juno's mission and aimed at some of Jupiter's moons, whose totaling then mission will include 42 orbits, or Parage Joves, by 2025, at which point NASA will deorbit the probe by scorching it in Jupiter's atmosphere to prevent possibly contaminating those moons. This process is compliant with NASA planetary protection rules, but it's of particular significance in Juno's case. Scientists have always questioned if life can exist on Jupiter's inner moons, and NASA doesn't wish to get dirty any existing or potential finds that may be discovered there. So on the 7th of June 2021, Juno conducted its close flybys of Ganem with a gravity assist to shorten his orbital period to 43 days from 53 days. Juno had previously done a flyby of Ganem in 2019 at a distance of 97.0 km, but this one brought the probe within a mere 1,000 kilometers of the surface of the moon. In this photo, taken by Juno cam, you can see almost half of Ganem's entire surface in stunning detail. To refer to the resolution is circa 1 kilometer per pixel. Iodore. The sharp rendering of Ganem's distinctive structural characteristics, you can almost feel its texture with your fingers. See how the icy surface is scattered with craters, light and dark patches, and long striations. The darker parts reveal older surface, which is highly cratered, while the lighter parts are relatively younger and less cratered. But what about those long striations? We know based on previous data that contains at least one vast salty subsurface ocean beneath its icy outer layer, which some speculate could be suitable for life. Scientists think that these long structural features might reveal faults produced by tectonic movements generated by heat from the moon's iron-nickel core, but this is a subject of ongoing research. This photo from the same flyby on the 7th of June, Gannam crater in greater detail. Why it looks so bright is that it's iced up. Here is another photo from the 7th of June, which I think is quite remarkable. It's a photo of Gannam's dark side and was taken by Juno Stellar Reference Unit navigation camera. The Stellar Reference Unit was created to maintain Juno on track with starlight, which renders it perfect for capturing low light conditions. For scale, their solution is 600 to 900 meters per pixel. Again, see the long striation sand craters, some of them stacked on top of one another. I have seen plenty of pictures of Gannam, many of which I have reported on before, but I am marred by how much detail Juno was able to obtain in these low light levels. Interestingly, one of the most unexpected findings from the mission came not from the orbiter itself, but from Hubble. Yes, that Hubble. Let me explain. You see, in order to assist Juno's exploration of the Jovian moons, NAS asked HBLE to monitor Gannam's ultraviolet signals. Gannam has an atmosphere, albeit a very thin one, and one of NASA's goals was to find traces of oxygen they long suspected was hiding there. Nearly everyone expected to find plenty of oxygen based on previous analysis of the moon's ultraviolet emissions, but much to our surprise, Gannam's atmosphere had very little oxygen in it. What they did find, though, was a whole lot of water vapor. This finding prompted a major overhaul of our model of Gannam atmosphere, and may imply that water vapor may even exist in the atmospheres of icy bodies all over the solar system. After flying by Gannam, Juno performed its flyby of Europa on the 29th of September 2022, which provided the probe with gravity assist that took its orbit down to 38 days. Here's a stunning photo from flyby, taken 351 kilometers away. It captures a section of Europa just above the equator. What I find amazing here is the day-night boundary called the terminator. The deep shadows really do enhance the ridges, troughs, and craters that puncture the surface of the moon, revealing it in nearly three-dimension relief. Researchers believe that Europa, unlike Ganymede, harbors a massive ocean under its surface, but recent research indicates there might be an awful lot more happening than the basic ocean crust model would lead you to think. What do I mean by this? Let's hold on to that as we examine the next image. This photo was snapped by Juno's Stellar Reference Unit camera and is a zoomed-in section of Europa's surface. It was captured at night on the moon from a distance of 412 kilometers with a resolution of 256 meters per pixel. This is the best resolution image that Juno captured of Europa. At a glance, your initial reaction would be, what am I looking at? Well, what you're looking at is a highly fractured area of Europa's surface, cross-hatched by grooves and ice ridges. That funny-looking dark spot just to the right of center might give valuable clues as to what's responsible for this geological complexity. Scientists think this darkened region indicates an eruption taking place beneath the surface ice. The thing is, Europa's icy crust is more than 10 kilometers thick. Think of the pressure would take to get through much. However, a recent paper put out by American Astronomical Society suggests a groundbreaking new theory, excuse the pun, with an alternative explanation. By the paper's authors, Europa's cryovolcanic activity reveals evidence of brine reservoirs locked inside the icy outer crust. This would indicate that way above the moon's subsurface ocean there might be lakes of high salinity brine, which slushes around, inflating surrounding ice like a balloon and bursting through every now and then. It's an intriguing theory, but to establish it, we might have to wait for the European Space Agency's Clipper mission that will arrive at Europa around 2030. I know, that's 8 years away, but it's not too soon to put your calendars aside. Let's return to Jupiter one more time. You see, whilst Juno was making flies by gamed and Europa, it also unraveled a large enigma, one that extends over 40 years ago. When the Voyager mission first flew by Jupiter in 1979, the probes picked up enigmatic flashes of light in Jupiter's atmospherescence, presumed that these were lightning flashes like those we have on Earth, so that would mean water would have to exist in all three states, solid, liquid, and gas, based on what we know of Jupiter's atmosphere. This would place the storms at least 45 kilometers below the observable cloud tops, though Juno refuted this theory, and the truth is stranger than imagined. Juno Stellar Reference Unit camera observed something strange 19 lashes at a much higher height than we imagined possible, with the extremely cold temperatures at this height reaching below 88 C. Science concluded that the storms were composed of ammonia water-based clouds, a phenomenon which doesn't occur here on Earth in these unusual and violent thunderstorms. The ammonia behaves as an antifreeze, creating a 2 parts water to 1 part ammonia solution that will not freeze in spite of inconceivably cold temperatures. And as far as anyone can tell, since these thunderstorms generate intense lightning bolts, they're showering down enormous hail composed of water, ammonia slush, and bizarre precipitation that scientists are referring to as mushballs. Jupiter is an unusual planet, and the more we know, the more unusual it gets. So there we have it, some of the best highlights of the pioneering Juno mission since we last checked. And the next stop for Juno will be Io in 2023, and for my money personally, I couldn't wait to find out what's in store. Juno has well exceeded my expectations every step off the way, and if Ganem and Europe anything to go by, our knowledge of Io is going to be a whole lot more exciting. Thanks for watching making this video. I'll catch you next time. Thanks for watching.